Let me, can you guys factor 24 for me? Give me all the factors.
1, 2, 3, 6, 8, 4, 3, 4, 6, 8.
Now real quick, why is 6 a special kind of number?
It could be factored.
I mean, not, let me see, how do I say this? 1, 2, 3, 4, but then 6 is like the start of the next part. Does that make sense to anybody? Because 6 goes with 4, right? So there's going to be how many total factors? 8. Is it, you with me?
Yeah.
Because there's 1, 2, 3, 4, and then there's the numbers that go with those, right? And real quick, what's the square root of 24? Isn't it at about 5, right? I think we talked about this really briefly before. Where's that turnaround point going to be around the square root of the number? And I really hope that kind of makes sense, because 5 times 5 would be almost 24.
Yes.
4 times 6 is 24. It's always going to be around that square root number where that turn point. Is everybody semi with me?
No.
I got it.
Are you cool with this part? Factoring 24, right?
Well, factoring 24, yeah, but then the 6, and then...
And the 6 goes with the 4, correct? Yes?
Yes.
So I don't even have to finish this. If I ask you how many total factors will there be, there's going to be 8, aren't there? Because there's 4, and then there's going to be the number that goes with each of those. Okay. Now,
Yeah.
our list has 2, 5, and 9 in it, and there's a total of 12 factors. Now, if 9 is a factor, what else is a factor? 3. And obviously 1 is a factor, correct?
Yes.
If 2 and 3 are a factor, what else is a factor? 6. How many do we have so far?
1, 2, 3, 4, 5, 6.
We have 6.
What about 8? Can that be a factor?
All right, listen. Everything, so in green is what the book told me. All right. 1 is obviously a factor of everything. 3, why did I put a 3 down? Because a 9 is there. Why did I put a 6 down? Because the 2 and the 3 are there. Okay. Allah. Good. So, what else? And how many do I have? Don't I have 6 already?
Yeah.
And aren't there supposed to be 12 total?
Yeah.
Okay, so, all right, this is as much as I'm going to say. There's that other half that you got to figure out. And what are you going to do? So if I didn't tell you this was 24, and I gave you this, you'd have to figure out 4 times something is the same as 3 times something is the same as 2 times something. You'd have to kind of tease out what that number might be. All right, I'm going to...
Tease that number? So,
Dude, yeah.
Like, so what do you mean by that?
This right here is like this piece. And then the rest of it is going to be the number that goes with 4 to make the end result. The number that goes with 3 to make that same number. The number that goes with 2 to make that same number.
So, I really don't get it. No.
Okay.
So, like, how did you get 1, 2, 3? How come you missed 4 and...
Did they tell me 4 was a factor? No. Do I have, now again, what did they tell me was a factor? Didn't they tell me those were the factors, right? That's all they told me. All right. Isn't 1 a factor of anything?
Yes.
Okay, so I can write that down because I know 1 is a factor of anything.
Yeah.
If 9 goes into the number, 3 must. So why did I write 3 down? Because they told me 9 goes into it.
Yeah, 9 goes into it.
If 2 and 3 go into it,
That'd be
6 has to go into it.
But then, what about 6 and 9?
What about 6 and 9?
I was gonna say like 6 times 9. Wouldn't that be like 54?
That would be 54, sure.
So
But-
wouldn't that be a...
No, you can't do that with everything. If 2 goes into something, does 4 go into that thing?
Yes?
No.
Oh,
Does
no.
2 go into 22? Yes.
So
Does
that's-
4 go into 22?
No.
No. So again, this is that idea. Stay with me, everybody. Stay with me. This is that idea Why did I say 2 goes in and 3 goes in, so 6 goes in? Why can't I do that with 6 and 9? Because, and this is why I'm so surprised always when they don't have this phrase. One of my favorite phrases we talked about the other day, those are relatively prime. So it makes sense, I can combine them and say therefore 6 has to go in. 2 means it's even, and 3 means everything adds up to be a multiple of 3. Since both of those things are true, 6 has to go in. Do you see how 6 and 9 are multiples of 2 and 3?
Yes.
Not together, but individually, right?
Yeah.
So just because 6 and 9 go in doesn't mean 54 goes in, right? Does 6 go into 18?
Yes.
Does 9 go into 18?
Yes.
Does 54 go into 18? No. All right.
How am I supposed to get the rest of them?
All right, now you're focused on what the actual problem is. And how much time have you been spending on the problem now that you know what it is? About a minute. So give yourself more time to think about it.
I don't know what else to think about it.
No. Don't say what else, because you didn't. Did anyone know this problem involved thinking like this?
No.
Maybe somebody did. If you didn't, and a lot of people just said no, just so you know, then now you know what to think about. And again, how much time have you thought about it? Not much. Okay. So anytime, I really want this to make all the sense in the world. Anytime I've got a number and I try to write all the factors, there is a special spot where I'm going to turn around. So 1 goes in, 2 goes in. Does 3 go into this?
No.
What's 5 plus 4?
9.
And 3 goes into that, so 3 goes into this. Does 4 go in? Hell no. Here's a quick way. You ready? Guys, doesn't 4 go into 48? So 4 goes into 52, doesn't it? You guys with me?
Yeah, no. I was just saying
So
no.
4 does not go into 54. 5 doesn't. What about 6? Yes, and see how 2 and 3?
Yeah.
And then what's the square root of 54 roughly? I love you guys. I'm not asking you for like the decimal. You with me?
2,900.
No, not squared. Square root. Don't even use a calculator. Stop.
It's between 7 and 8.
Good. Isn't 54 between 49
and 64.
and 64? So therefore the square root's between 7 and 8. So that, are you guys with me about this right here?
Yes.
There is a turnaround point where you start pairing them up. So 7 doesn't go in, 8 doesn't go in. 6 times 9 is 54. Of course I had to pick 54, so now you're going to go, oh, all right, it's okay, Jeff, it's okay. And then 3 times...
So I'm looking at 12 to get into my 12 factors.
Yeah, so we got the first 6. So now this is going to be the... So whatever number's here, 9 times it is the answer. Whatever number's here, 6 times it is the answer. And so forth.
Like 9 times it. So what I say 9 times 5 would be 45.
Because look here.
Okay.
Look here. Isn't 6 times 9 54?
Yes.
What's the number going to have to do that I put right there? What's it going to have to do?
Get bigger.
It's going to be bigger because so 9 times 6 is 54. That's why I put a 9 there. How do I figure out what goes here?
Times
3 times what is 54, right?
Oh.
So that's what I'm talking about here. That's what I'm talking about up there.
So basically we're looking at like I'm gonna have to look at 9 times what goes into 45, and that's 5.
No 45. Where'd 45 come from?
Because I'm just confused by the first box. I'm like, well, how did you get all those numbers? In the first place.
Oh, here?
Yes.
Oh, we just went over that together. You helped me with some of those.
No.
You totally did. You totally did. So again, one more time and that's it. Isn't that what the book told us, right? 2, 5, and 9.
Yes.
Okay, 1 goes into anything, so I can write 1 down.
Okay.
Okay, if 9 goes into it, what else goes into it?
3.
3. I mean, see, you're helping me again. If 2 and 3 go into it,
2 and 3.
what else goes into it?
2, that's 6.
6.
But if 9 goes, but then what else goes into it? 9 times 3 goes into it.
Now watch this. Now you can do this. Let me see. Where's a good? Let me see. Relatively prime. I need somewhere that's relatively prime. So remember the whole idea. This is why this is such a huge idea. Let me give you a little clue. Are 3 and 5 relatively prime?
Yes.
Yeah. So don't 3 and 5 both have to go into the number?
15.
So 15 has to go in. Are 5 and 6 relatively prime?
5 and 6. Yes.
Yes. So 5 times 6 has to go in.
So that's 30.
What was this number again? It was 24, right?
Yeah, it was 24.
All right, now watch. Man, it looks like I'm diagramming a football play up here. Jeez. All right, stay with me. Now, real quick, we can finish this out, right? 6 and 4 is 24. 3 and, thank you for that, 8. 2 times 12. And of course, 1 times 24. Now watch. Aren't 3 and 4? Is everybody cool with this phrase? I know it's not in the book. Is everybody cool with my phrase, relatively prime?
Yes.
3 and 4. 4 is not prime. But 3 and 4 are relatively prime because they don't share any factors except 1, right? So therefore, 3 times 4 should go in, and sure enough, freaking 12 is there, right? So what am I saying? When I say 3 and 5 go in, so 15 has to go in,
And 8.
isn't one of those numbers going to be 15?
Yes.
Yeah.
One.
If 5 and 6 go in, then 30 goes in, isn't one of those numbers?
Yeah.
5 times. So I just put 30 in. Or
So, I mean, okay, that's, I'm not going to say any more.
5 and 6. And then
I like
9 and
that.
15. 9 and 15 are prime, right?
Say again?
9 and
No.
15.
No, they're not relatively prime, because they both have a 3, right?
No.
Okay, I like it. How you guys doing here?
Not really great.
I'm chilling.
Okay. All right. Anything else from homework?
Number 33.
In that same section?
Yeah, same section.
Smith number, love it. Oh, geez. Okay. I wonder if my old colleague, she just retired, Beth Smith. I gotta ask her if she knows about Smith numbers. Is a counting number the sum of whose digits is equal to the sum of all the digits of its prime factors? Holy shit. So a Smith number is a counting number where the sum of all of its digits is equal to the sum of all of the digits of its prime factors. So for example, 24, the sum of its digits is 2 plus 4 is 6. But if you add up all the prime factors of 24, you get a lot more than 6, right? So that's obviously not a Smith number. So here, all you gotta do is, all you gotta do. But, so you're gonna find all the prime factors of this. That's gonna be the hard part of this. And then you just do what it tells you to. Yes, maybe? You guys all right?
Because what I tried to do was factor that whole big
Yes,
number.
of course, you have to. I like it. And what's the most obvious thing that goes into this number?
5.
5.
Well,
I love it.
5 times 9, 5, 8, 7, 5, 5, 5.
It ends in 5 again?
Yeah, that's in 5.
So what goes into that number?
5.
5.
And
So there's
then,
another factor of 5.
and then it goes, and then it times 1, 9, 1, 7, 5, 1, 1. So, and it goes, and I noticed that's a relatively a prime, so it can be multiplied by 3.
Oh, you mean if you add up, all right, so again, yeah, if you add up all the digits, do they add up to be a multiple of 3, all that kind of stuff, right? So you can start to break this thing down.
Now the last part I couldn't factor was this number. I got 3, but then it can be multiplied by 6, 5, 8, 3, 7. Now, I don't know what it could be, well,
Yeah, and let me do this better this time, because I just realized, let's do a problem for real here. So, looking at 24, if I break 24 down into its prime factors, right, 4 times 6, 2 times 2 times 2 times 3, is that cool?
yeah.
What's 2 plus 2 plus 2 plus 3? 2, 4, 6, 9, right? But 2 plus 4 is 6, so that's not a Smith number. Because its prime factors don't add up to be the sum of the digits of the number itself. Sum of whose digits is equal to the sum of all the prime factors. So the biggest, hardest part of this problem is going to be factoring this thing down in a factor tree, but that's actually, you've already told us the first 2 steps, divide by 5 a couple times. Yeah.
And this is what I got so far. Can I show you? This is what I didn't know how to factor this number right here.
Well, let's see, 6 and 5 is 11, plus 8 is 19, plus 3 is 22, plus 7 is 29, so that means 3 doesn't go into it.
Yeah, no. 3 doesn't go into it.
What's that?
I put it, you said 29.
Oh, yeah, they added up to be 29.
Yeah, they added up.
Yeah, so just try to divide it by, I mean, obviously it's not even, right?
Yeah, no, and I don't think 29 can go into 3.
No, yeah, definitely not. But try to divide it by 7, try to divide it by
Try to divide it by
11.
11. Nope.
Okay.
And 11. What else?
So that might be prime.
It might be prime. Yeah, I think that is a prime.
If that's prime,
It's not good. It's not a
I
relative.
really doubt that that's prime. Yeah, so I'd make sure.
The calculations sounds like
Wait a minute, what are we? 18, 24, 25. Did 3 went into this?
yes. Well, I can try again if you want because that's what we did. 19175, and this is with the tutor. And I'm like, are you sure?
It didn't go in, right?
No, it
Okay.
didn't. Maybe I wrote it wrong. Maybe.
No. Oh, well, yeah, double check your numbers when you do the division. Okay, but at least you know what to try to do now.
Yeah.
Okay, Mike.
For 5.2b, 13, I think there's a typo in letter C.
It's a really good chance. Which one again?
It's 5.2b 13c. It's technically the second part of it. Yeah, it's a 7, 6, 11, 4. I think there's supposed to be a multiplication, but I think that would work anyway.
Yeah, that.
Oh, yeah, I see what you
Yeah.
mean. Yeah, you're right. There should
Okay.
be a little dot there. Yeah, okay.
Yeah, that was a little typo. I talked up with the tutor. We saw a bunch of typos when we were doing the homework, and I let them know about the key answer, so it really helped them.
I like it.
Let me see where am I?
Anything else?
Um,
Okay, so it definitely always sucks whenever there's a typo. And then some of these, it takes a couple of readings just to figure out what it's really asking you. So that I can relate to, obviously. You just saw it happen in real time. All right. If there's nothing else, let's get back. Well, actually, let's do this. I want to show you a video from, just one video from the last section we did. Let's see which little person we get this time. No, not there, Jeff. Let's go here. All right, so let's see.
Okay, what I would like you to do, I'm going to write down 2 numbers, 18 and 24. I would like you to write some of the factors. Just write a few factors for 18 and a few factors of 24. You know what I mean by factors?
So like a factor tree or?
Sure, factor tree would be great.
Okay.
Now, I have a question for you. So you have some factors listed there. What is the greatest common factor?
2, I think. Well, because.
They need to get a better cameraman. He's gonna zoom in a little bit here in a second there.
So how do you know, you think you've got all,
Alright, so real quick. I mean, isn't this what I was just doing, right? And this kind of completes the whole picture. Oh, it is 24, it's funny. That these 4 go with these 4 and so forth.
factors for both of the numbers?
I think so. Oh no. So it'd be 3. I'm pretty sure.
So what are you looking for when you're looking for the greatest common factor?
Well, because like you don't have factors, so you would, you would like try. So you write down all the factors and then just see how many they have in common, or
Okay.
like what one is the same but it's the largest.
Okay, so why don't you go ahead and list all of the common factors for me?
So real quick, you can tell, obviously, is she correct? No. So I don't often, well, I don't want to say that. Sometimes I disagree with what he's asking people, but I like how he's trying to make sure to tell her, show yourself exactly what it is you're trying to look at, right? So what he's going to ask her to do now is to actually, that set intersection method. You remember talking about the set intersection method where you wrote all the things and then you wrote all the things that were in both? That's exactly what she's about to do.
Yeah, 1, 2, 3, and 6.
Okay, so what's the greatest common factor?
Great, 6. Wow, I'm smart.
Okay, all right, you got it. Thank you very much.
I like that. So, I mean, when she said, "Oh, I'm smart," what do you think that was?
Sarcasm.
Yeah, sarcasm for
That's
herself.
messed
Yeah.
up,
A little self-deprecating thing, like, "Oh, geez, I'm really smart." Okay, I like it. Okay, let me see. I want to do the other ones here after we talk about some stuff. So let me turn you on. Go ahead. And then, whoever's not here today, you missed out on all that. So, we're getting into fractions now. So let me ask you, let me see, what order do I want to do this in? Let me ask you something that seems really strange. What is this?
12 divided by 3.
Totally. 11. So what does it represent? Can somebody give me a problem that would lead to this that has to be done to get the answer? You guys remember we actually had exactly that question on a few homeworks a while back? So give me one problem that would lead to a student needing to do this.
Will we make a problem?
Yep.
There are 12 slices of pizzas, but there are only 3 students, but they want to have lots of pizza. How many pizzas can be divided to?
Or how many, all right, let me help out a little bit. How many slices can each get?
Yeah.
Okay. Right, exactly, right? You got 12 slices, you got 3 people, how many slices can each get? I like it. So, one way to think of this is, we all know the answer to this problem, but the number that is the answer to this ratio represents what does it take 3 of to make 12? Right? All right. So obviously that number, we know that number is 4. That's amazing. So now what I really want you to get from what I just said, that's what basically every ratio means. Right? So 12 over 3 is the number that it would take 3 of to make 12. So what does this ratio mean? So again, this ratio, the answer to this ratio is the number that it would take 3 of to make 12. That's what that means. Right? So what does 1 over 7 mean? Let me put the,
Seventh of the whole.
no, now you're trying to go beyond. So now there's a lot of different ways to look at fractions. This is one of the most basic ways to look at them. And I really doubt that anybody's ever shown you sort of this kind of direct way to look at it. Is everybody cool with what I said up here? There's a number that 12 divided by 3 is. We can write it down pretty easily. But what does that represent? It represents what it takes 3 of to make 12. So what does this number represent?
7 of.
What it takes 7 of to make 1. Yeah, there, that's it, right? And of course, our brains kind of balk at that. Yes? Do you guys agree with me that your brains balk at the idea of fractions a little bit? But if I had, so if I worked on an assembly line, right? If I worked on an assembly line, have you guys ever seen I Love Lucy? No? Where little chocolates are coming down. And I gotta fill these boxes with chocolates. And it takes 7 chocolates to fill a box. How do you spell the word chocolate? I think that's... Don't laugh at me. Well, you can laugh at me, that's fine. So if it takes 7 chocolates to fill that box, oh, let's see, now I've lost my thread. I don't know what it says. Once you get that filled, that's 1 complete box, correct? So of course, how many chocolates does it take to fill the box? 7. Okay, all right, maybe. So let me make this connection better. So 1/7 represents the amount that it takes 7 of to make a full thing. And that you kind of know. I know you kind of know this. If I break this up, 1, 2, 3, 4, 5, 6, 7. And every step then is how big. So another way to represent a fraction is to do this. How big is this step?
1/7.
1/7, right? And this will be 2
7.
7s.
3, 7, 4,
5,
5,
6, 7. So now you can talk about it as steps. How many steps will it take to get to a full 1? If every step I take is 1/7, it would take 7 steps to get to a full 1. All right, let me stop for a minute. Stay with me now. Has anything I've said yet been really, really strange or not made sense?
No, not yet.
Not to, I mean today, by the way. Today. Not for the entire time you know me, because you're like, I've got a list of shit. It's basically all my notes, John.
Just about about the homework, that's it.
Don't worry about it. Not yet. You don't know what the hell it's going to look like yet. Okay.
No, I mean the homework that I was working on.
Oh, that one. All right, let go of that for now. All right. So one way to think of, to kind of like talk about fractions, do you see why would I start here? Because by the time we talk about fractions, you talked about division. You talked about all the different ways to think about division, right? And a fraction is just a ratio, much like division is a ratio. And at this point, they've divided things that go in evenly. They've divided things that had remainders, possibly, right? Big ass R notation. So every time you try to introduce a new idea, you try to figure out, can I base it on something we've already done? So let me ask again. Do you guys understand what my point was here, right? This does equal some number. That number is how many 7s it takes to make 1. Okay, maybe. All right. So that's the first little thing.
Would it be a decimal?
Totally, it's gotta be a decimal. In fact, 1 divided by 7, is it gonna be a pretty decimal?
No.
Pretty? Like 1/4, 1/4, is that a pretty decimal?
Yes.
Yes.
Why would you say it's, some people like,
It would be 2.5,
Yeah.
like 25 cents.
so even if you kind of disagree that it's pretty, is it prettier than 1/7 would be as a decimal?
Yes.
So why is it pretty? Because it stops, for one thing, right? And it's only 2 places, I mean, come on. It's hard to beat that. Okay. So, the really classic way to deal with fractions is, of course, to have something like, coming back to Andrea, like when you brought up the pizza thing, pizza's good because that gets people attention. And no, there's no pizza in the back room, sorry, too bad for you. Ha.
I don't know.
Looks like
What is pizza?
So how much of this pizza is shaded?
3/4.
3/4. How did you know that so quickly?
Cause I remember
pieces,
elementary.
and there's 3.
Alright, so let me ask you this.
left.
How much of this pizza is shaded? It's still 3/4. I missed that.
It is.
Oh,
I think you see my
I didn't
point.
know if you were.
I got it. It's
purposely
weird to
drawing
try to
it.
draw this in strange, here we go. I'll do this. Oh, so I'm really sure. Alright, so how much of this pizza is shaded? Aren't there 4 slices? Aren't there 4 pieces shaded? I mean, sorry, 3
Yes,
pieces shaded. Is 3/4 of it shaded though?
no.
No. Do you understand how that is a point that a student could easily miss
Yes.
Yeah.
if you don't make it really obvious?
Yes.
So let me ask you this. What's the difference between these two, of course?
That someone don't know how to slice it.
Yeah, this is somebody's like, I can only have 1 piece.
Oh my.
So that's mine, I just have 1 piece. I'm gonna diet. Alright. There's a word. So these, obviously, every piece here is what? And every piece here is not what?
Even.
Evenly, okay, I like it. Evenly sliced, they're not equally. So these are equivalent
Equivalent.
subdivisions. Equivalent subdivisions, dude. And these, of course, are not equivalent subdivisions. Okay.
Yeah.
Good.
Yeah.
So this is a really good example of little things that if you're not careful, if you never say it, they're not gonna realize it's something to even take into consideration. You could do several problems like this, and they just focus on the fact that there's 3 pieces. So here, there's 3 pieces shaded, out of 4 pieces, 3/4. What's wrong with that? Well, there's a lot wrong with that. Yeah. Okay, I like it. Now, obviously, it doesn't matter what shape you pick. I'm almost certain you guys can remember, I mean, you could have this. So how much of this is shaded? Well, shit, now, pretend like it's equal. This is me drawing, so.
1/4.
1/4, ooh, now, so that's 1/4. So what if I do this? Kind of like they're all equal. Yeah.
2/8.
2/8. And what do you think that's illustrating?
The 2/8 is equal to 1/4.
Yeah, 2/8. So 2/8 must equal 1/4. Something we all know. What did I do when I drew that line?
You cut it in half.
So before I drew that line, how many of the pieces were shaded? 1. When I drew that line, how many are shaded now? 2. Now I understand they're obviously smaller, but we just care how many, right, are shaded. How many total before I drew the line, how many total parts were there? 4. After I drew the line, how many parts were there? 8.
8.
So I doubled the amount of things that were shaded, and I doubled the total amount of things there were, right? And I know, trust me, you guys, I understand that you all know this, but this is an interesting way to show if I double the number that are shaded and I double the number that I had total, that makes an equivalent fraction. right? Okay,
I think
amazing.
they-
Yes.
In like elementary school, they call the thing that's between the two fractions of a big one. That's what they.
Oh,
call
yeah,
it.
yeah. In fact, one of my colleagues, let me see if I can do this. Oh, you already know how bad I suck at drawing, but let's see, can I do this? She actually makes a big ass one. Maybe you can understand what I'm trying to do? I don't know.
Absolutely.
Thank you so much. You don't know how much that hurt me to try to do, okay. It looks like a shirt where I lost the sleeve, I don't know.
A dress without the sleeves.
Huh?
A dress without one of its sleeves.
Sure, one of my many dresses that I have. Yes. All right, so I like that. Yeah, that's a big ass one. So that, there's a beautiful connection between the visualization of a problem, actually slicing it in half, and they can see there's 8 parts now. They can count the 8, they can count the 2, so they get the 2 8s. And then you say, well, that must mean, did I shade any more than I did before? No, so those must be the same. And then you sort of work towards the idea of this is 1, like you said, so when I multiply by 1, I don't change, but you don't want to start here with a little one, right? But that's a great way to kind of come at it from a more visual place. Okay, maybe. All right. In case you're curious, I'm not even gonna try to pretend as if I knew this before I saw it in the book. But can you guys remind me, what's the official name of this number up here? Numerator.
Oh,
Denominator.
denominator.
Denominator. Okay. What was that? That was really funny. All right. She had her own little rap thing going on. Okay. On page 210, I think, if you ever were curious where those names came from, they tell you. So if you're not curious, just never look at page 210. But on page 210, they tell you. Very interesting. Denominator comes from nomenclature, which I had no idea. Have you ever heard of the word nomenclature?
I don't remember where. Oh, English and chemistry.
Yes, English for sure. Yeah, chemistry too. Yeah, it's all about how you name things. That's really what it is. Okay, I like it. Just wanted to mention that. We already did that one. Oh, okay. Here's another. Here's a callback to earlier. If I take this and I break it into 4 parts. How much is in each part, right? 3, obviously, right? So that's another way to get that to 12 divided by, I think I had 3, but you got what I'm saying. It's another way to get 12 divided by 4 is 3. So you can do the same thing here. If I break this into 7 parts, how much would each part have? So up here, if I break it into 4 parts, each part's gonna have 3, right? 1, 2, 3, blah, blah, blah. They're all gonna have 3 in them. So how much is this? If I break this into 7 parts, how much is it gonna have in it? 1/7 each. Blah, 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 right? And again, there's so many representations of fractions and where they come from. One thing I wanna, where's that gonna be? Yeah, okay, let's do that real quick. So, let's try something a little less specific. What if I break this into B parts? If I break it into B parts, meaning 7, 8, 9, I don't know, just B. It could be anything. It could be 4, it could be 3, it could be 28 million. How big will each part be, of course? 1 over B. I like it. Blah, 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 blah. So what does this, so what would this be? Yeah, because I've taken 2 steps. Each step is 1 over B. So 1 over B. 2 1 over B's is 2 over B, right? So forth. So what does A over B mean? in this context? What does A over B mean? Well, what did 2 over B mean? Took 2 steps, each 1 over B big, right?
Take A steps.
A steps. So if I take, get in there. If I do this, A times, I'm going to end up at A over B. Okay, again, nothing groundbreaking. They would, at this point, they would definitely be used to number lines. They would be used to stepping around on the number line. This is making sure they understand a normal number line. How big is each step? 1. Does it have to be? At this point, do you think you would have talked with them about multiples?
Yes.
So could you ask them to create a number line that steps by 3? Right? Okay, I like it. So now we're saying let's create a number line. So then you could say create a number line that steps by 1/2. And of course that might be nothing you don't want to do too early, but you could certainly do it. 1/2. And then another half would be 2 halves, which is 1. So forth. And again, it's building on what they already are used to doing. Working with number lines, stepping around on the number line. Okay, I like it. All right, here's what I want to do this. Beautiful. So, let me ask you this. Let's go back in time a little bit. What number does that represent?
3.
3. It's amazing. What number, so this is part 1, yes? That represents the idea of 3, number that we choose to represent as 3. That symbol 3. So in Chinese, ancient Chinese, it would have looked like this. Right? In Mayan, it would have looked like this. Yes?
Mm-hmm.
All right, so again, number and numeral, 2 separate things. Number is the idea, numeral is how you capture the idea. Just like words. There's an idea of snow, and then you have words that capture that idea. I'm not sure why I picked snow. So, what numbers does this represent? 3. Okay. No, you're all like, what the shit is this guy's pulling? Right? This still represents 3, correct? Would you say that this 3 is bigger than that 3 or something?
No.
That would make no sense, correct? Okay. So, I want you to understand the trouble students might have. So let me ask you this. What does this here represent? What fraction?
1/3.
1/3. What does this represent? You could do it, Jeff. 1/3. Isn't that a lot bigger than this? Do you think, since we use visual aids much more with fractions, we don't use a lot of visual aids with 3, correct? You guys semi with me? Don't we use a hell of a lot more visual aids with fractions? You know this. There are aspects of the visualizations we use that students can get stuck on. And they can start thinking about size. So you could say, well, is that fraction bigger or smaller? They say it's smaller. No, it's equal. So what the hell then? Why is that not a big deal? Why is this not a big deal? Why is that 3 not bigger than that 3? Because what is it doing? What is that 3 doing? What is the only thing it cares about? Quantity. I love it. It's just counting. So, what does this 1/3 care about in each case? Okay. So let's put that together. The relative amount. Relative to the whole thing, how much is shaded?
1/3.
1/3 in each case. I like it. So, this relates to something later. Let me see, do I want to go through the whole example? So do y'all understand that 10% doesn't necessarily equal 10%? Do you understand that, what I'm saying? Let me ask you this. Okay, let me go through it.
Oh, yeah.
What if I got my pay on my check let's pretend like, okay, Jeff is making $10 an hour, right? And let's say I get my check and I realize they sliced my pay by 10%. You guys with me? And like with no warning, I you know, if I suck, they didn't tell me. Are you with me? So, can somebody tell me how much I'm making now an hour? I was making 10 an hour. Now I'm making 9 an hour, right? So I go complain. Is everybody with me?
Yeah.
I would too.
Of course, yeah. Isn't that the thing to do?
That's
So
a
it's like, what?
rip off of your minimum wage.
I'm a teacher, and you're killing me.
Yeah.
I'm like, oh, we're sorry. We'll raise your pay by 10%. Should I be okay with that?
No.
No.
Hell no.
I would not.
Why not?
Because
The first 10% was based, yeah, exactly. The first 10% was based on $10.
Now you're showing 9.
Now, if they increase me from 9, what's 10% of 9? 90 cents. I'm back up to $9.90. And that dime adds up over time, yes? All right, I know nowadays, back when I was making $3.25 an hour, and I got a dime an hour increase, I was like, oh yeah. I mean, it meant a lot more. So, I want to tell Bill both ways. I'm sorry.
Oh, yeah.
Oh yeah. But here, this doesn't come into play because we're not talking about the area of this, yes? That's not what a fraction represents by itself. It just represents the relative amount. Yes?
It's when you're talking about the percentages of your raise or de-raise, I don't know. It was like, I thought of when they take out taxes, but depending on how much you made, that check it would change.
Oh, I see.
Because
Yeah.
I don't know the percentages of what taxes or how old you are or whatever, but you know. It's something like that.
Are you talking about like the Social Security tax?
Yeah,
and the
like when they take out your
Medicare?
taxes,
Okay.
it changes based
Now,
on
of
how much
course, the federal income tax is based on how much money and so forth. And real quick, did we talk about, since it came up, did we talk at all about income tax? Do you guys understand that if you make $1 more, your whole amount doesn't get taxed at the higher bracket? It's just the amount that's over. So much of the shit that comes out of certain politicians' mouths are based on the fact that they know people don't know math. So they all get it, oh my God, it's terrible. No, I'm really sorry. Maybe later this semester we'll get deeper into it. Go ahead.
I'd like to.
What I'm sick of is like if you get like a part-time job, you have to pay taxes.
Okay.
Yeah,
Yes.
that's what
You have to
one
do that
thing I
now.
learned when I had a job, and
Yeah.
my parents were like saying, Andrea, you're gonna have to learn to pay taxes.
But if you make underneath a certain amount, you should get all that back.
Like, what if you make minimum wage?
It depends on what you work too.
Yeah.
And if you're independent.
So
that's
I
depending
can't remember what it is. It's like 10,000 or something, or maybe it's 50. I can't remember. Somewhere down 10 to 15, somewhere in there. If you make below that much money, you get all your taxes that you paid back.
Last year, if you were single and dependent, it was like you made 12,000 over
Okay.
the year, or like 12,000 over that year. You had to file for taxes, but I don't know what it's going to be.
Yeah,
I feel
every
like
year
it
it changes,
changes.
of course. Yeah, because inflation and all that kind of stuff. Yeah. Okay. Enough. I'm not a business teacher for damn sure, but I do know a few things, and they trouble me when not everybody knows. Okay. So coming back to fractions. I know. Let's see. I kind of talked about a little bit of this already. Oh yeah, I did that earlier. So here's a kind of a weird thing. I can represent fractions with a circle, yes, like we just did. So this, of course, would be 2/3. I could represent it with a rectangle. This is still 2/3, yes. I could represent it, how do I want to say this? I could represent it like this. Let's see if you guys are cool with this. This is still sort of like 2/3 in a way. It's kind of a weirder way to do it because we're used to having one complete picture. So the shape that I pick, the choice I'm making is the choice of region model. Holy, it's just the word we use. So the region model is just picking what shape I want to use to represent my shaded parts and fractions. Okay. Let's do this. Let me see. Let's see if I want to do this right now. I think so. This one's kind of silly. Oh, that's all right. We can do this. Okay, let's do this. So we got this here. Just barely anything up here. Okay. I finally figured it out. Just gotta wait for a second, and then it's okay. Okay. Boop. So this is gonna be semi-interactive. Let's see. I think some of these are pretty decent. Yeah, this one's especially cool looking. All right. Panasonic. There we go. All right, so this is not, you can imagine this being a decent little exercise for a student first learning this. So it wants me to represent this fraction in this picture. Can I currently do it the way the picture is? Not very well, right? So of course I can pick how many pieces to subdivide this region into. So of course, how many pieces do I want to?
17.
Holy shit. And then I get to do
Oh.
4, 5, 6, 8, no shit.
Just subtract 2.
9, 10, 11, 12, 13, 14, 16, 15.
Wait,
There it is, 15, okay. Thank you so
Wait a
much.
minute, I know one.
So just keep 2 unshaded, thank you. And then good job. Now, the region model, if I do a new shape, it might give me another circle. Let's see what it does. Nope. So now I want 19 out of 19.
Got it.
Now this, this is exciting. I wish I could just slide it through. Screw it. We all get the idea. Why 19 out of 19? Why would you do that to me? Now, of course, when you have this, the kid do it, you're like, did you fill in the whole block? Yes. So that's one block. Yes. So the 19 out of 19 is one whole thing. Okay.
could you just like lower it down to 1? Because that is 1.
So again,
I mean,
sorry?
if like, I guess no, because it says 19 out of 19, but yeah.
I want to see what it says when I get this wrong. Let's see. Oh, you have the correct number of total division. Oh, that's nice. Let's make that wrong. Let's see what it says. Check the total number of pieces. Okay, all right. Anyway. Now what about, now this is exceptionally cool, and this is what we're going to work with probably next time, but I just want to kind of lay this out for you.
Geometry.
Dude.
Let's go.
All right, let me see. So this is one complete hexagon. And you can do stuff. You can click it, click. And it goes, all right, now watch this. How much of that trapezoid, how much of that hexagon is this trapezoid?
Half.
Half of it. I love it. So if I gave myself another one, flipped it. Shaboo! Very nice, very nice. Okay, anyway, so we have yesterday, not yesterday, but you know what I mean, the other day. I had these out here, I thought we'd do a little bit of a preview of them. And then I decided, no, I could just use this thing. You're gonna actually get to play with them next time, and we're gonna do some problems. And they're gonna be a lot like, remember when we did the base, was it the base 5 pieces we had? I can't remember. Remember we had the little flats and the longs and the cubes? And every time you put them together, if you created a long out of little individuals, you put them in the next spot, right? Fractions are the same because they're a part of a number system. All of our number system has to work the same way. So if I have little 10th pieces, how many of them will make it so that I have to put it in the next place? If I have little tenths, how many would make 1, of course? 10. So if I have 10 tenths, then I can just replace that with a 1. So it goes into the next place. Okay. And then we get a rhombus. Boom! Now, of course, what would you guys call that?
Diamond.
Diamond. If we look at that, and it's a rhombus. It's like a square somebody sat on. So the rhombus, how much of that is the... Jeff, you could do it, buddy. There. What do you think before I do the rest of these? Yeah, so I mean, that's thirds. So isn't this a little better than just shading pictures? And you can actually combine, like if I had 4 rhombi, oh yes.
Is it really?
I had 4 rhombuses, we'll just say that. how many what would that be? Because 3 rhombuses is 1 piece. So what is 4 rhombuses?
4/3.
Yeah, you could do 4/3 because they're each 1/3. So 1, 2, 3, 4/3. Or you could do 1 and Jeff.
1/3.
Oh, that's neat. Yeah, I love how excited you guys are.
Look, he did something.
Or I could do 1 and 1/3, yes?
Same
Okay, that's the connection between improper fractions, mixed numbers, right? Okay, I love it, I love it. So of course these are little manipulatives. Manipulatives are huge, right? Little kids love this shit. They like to move it around. Even if it's math, they're still like, oh, cool. To be really honest, all right. We do have one last piece that makes sense here. What's up with a triangle? How many triangles are gonna make this thing up? Yeah, triangle is 1. Can I get the triangle? No. Give me the triangle, okay. So I need 6 of these things to make that shape. All right, anyway, so we're gonna have these to kind of play around with on our desks. Let me see, did I wanna do anything else here? Was this okay? No, it's the same thing. I think that was all I wanted to do right now. Yes, that's all I wanted to do right now. I love it. All right, let's go back. Sorry, little dude. All right, so let's get a little more technical. And then we're actually going to leave a little early today. Hopefully that doesn't bum anybody out. You guys okay with that?
No, we'll go with that.
I had a feeling it'd be okay. All right,
Sorry.
a little more technical. How can you tell, oh man, poor little dude, if 2 fractions are equal? Become a thing. Right. So like if I had, if I just had a fraction and another fraction, what would I do to tell if they are equal?
LCD. Find the least common denominator, then.
True, there's a shortcut. There's a shortcut.
I don't remember. Well, I was never. I just remember the first one.
I understand. So like, for example, this is true, right?
Yes.
What do you notice about this?
They equal the same.
When you multiply, don't they equal the same?
Cross multiply.
Cross multiply, yeah. So if you multiply 6 and 1 and 2 times 3, they equal. So any fraction that is true for, any 2 fractions that's true for, those fractions are equivalent. They're equal to each other. What's up? Oh, thanks, man. And this kind of leads, let me go ahead and talk about this a little early. Why not? So let me ask you this. Are these equivalent? Can you guys just tell me the answer? Are those equivalent? Can you tell they're not? All right, do the test real quick. Show me what you get.
$77 and $72.
77, 72. I like. So bring the 11 up to here. Bring the 8 up to there. What's true about these? Which one's bigger?
77.
So guess what? That's true then. 7 eighths is bigger than 9 11ths. Okay. So this is kind of nice. That same trick, not trick really, but the same method of multiplying like this and multiplying like that. If they come out equal, then the 2 fractions are equal. If they come out any other way, that same thing is true for the fractions. It's really, really nice. Okay. So. Let's see. Which one do I want to do? Let's do this one, yeah. Oh, this one, all right. So, can you guys just real quick, how would you reduce this?
Divide by 3. 6.
Well, let's divide by 3. Why not? How does this relate to something we did earlier? If I write it like this, how does it relate to something we did earlier? Anybody remember? You're like, I live in the now, dude.
Like earlier today or earlier past
today.
lesson?
Earlier today.
One.
Remember when I had that
The big
picture of
one.
1/4 and I cut it in half?
The
So I
big one.
doubled and doubled and you told me this is a big ass 1, right?
Yeah, that.
Okay, well you didn't say big ass 1, but. Isn't that exactly sort of the opposite of what's happening here? I can take this away, somebody else brought in a big ass 1, so I can take it out of there. If I can put it there, I can take it out and go the other way, right? And of course, I'm not done, right? 4 is 2 times 2, 6 is 2 times 3. Shabam! Now, how many of you would actually do that problem this way? Probably very few of us, right? We don't need to. Yes.
If you want it in fraction form, I would do it that way, but if it could be in decimal, I just do it.
Decimal, no. Psh,
No,
Can't
no.
go with that. That's better shit. Right? We're better than that. So yeah, but again, I don't think, do any of you reduce fractions like this? Actually showing yourself?
Sometimes.
Do you understand how, if this is pretty new to somebody, it's a great connection to make with earlier stuff? And again, that's one huge thing about math. It's all about making connections. Do not treat anything you're talking about as if it's brand new. It's somehow connected to something else, or else how the shit would they ever learn it? It's got to be connected to something they already know. So you got to find those things and connect it. I know I've had horrible math teachers in my life, earlier in life. I had worse English teachers, or else I might be an English teacher now. I always wonder about that, right? I had great math teachers later. I'm like, what if I had great English? Maybe I'd be an English teacher. Who knows? And some of you guys are like, I've heard you, Jeff. I don't think so. I'm like, all right, thanks. Thank you so much. One thing to notice, and this is something I brought up many times before. How far apart are these? 6. So if it's going to reduce, it's going to reduce by some factors of 6, or maybe 6 itself. Does that sound at all familiar? So what about that? One thing you could do is just keep dividing by 2 until one of them's not even anymore, right? Does anyone ever do that?
Mm-hmm.
Just divide by 2, divide by 2, divide by 2 until something's not even. You could do that.
Yeah.
I love this. You guys are doing something. What are you guys doing? Do you know where your convert to fraction button is on your calculator? No? Okay, I just gave it away. There's on a lot of calculators, there's a convert to fraction
It's
button.
2 over 5. It's 2 over 5.
2 over 5? Is that what you guys got?
I haven't finished yet.
Oh, okay.
Because what I did was what you suggested, divided by 2, then
Okay.
divided by 2, which would
I
be
got
2
0
over 5.
Right, and then here, divide by 2 again. Divide by 2 though, watch, divide by 2, you don't get 3 over 5.
Oh yeah, 3 over 5, my bad.
I lie.
So we could actually divide it by 16.
I lie, got it
That's
all.
weird.
So what did we end up, yeah, exactly, I just heard it. What did we end up really dividing by?
16.
16.
I started off by subtracting 48 from 80 and got 32. That's why I
Beautiful, yes, I was,
started
okay.
off with 8.
Look at somebody applying the thing I said, it's amazing. So they're 32 apart, right?
Yeah.
32 does not go into either of
But I
those.
knew-
So try the next factor 32 down, 16. And sure enough, 16 goes into both. So whatever distance they are apart, if anything is gonna go into both, it has to be something that fits in there, right? Some factor of how far apart they are. Because then that would match up with the multiples that it would count by. If there is nothing, then it's not factorable. What do I call it? What form is this in now? What is this called?
Simplified that.
Sure, simplified, simplest
Form.
form, reduced form, whatever the shit. Right? however you're feeling that day. Lowest terms, have you guys heard that one?
No.
Okay, let's see. Last thing. Did I already say last thing? Too bad. One more thing. Let me see. Yeah, that'll be fine. Yes. How do you make this? What's kind of weird about this fraction?
Improper.
Good.
Do they still use that word?
They do. We do.
Okay.
Improper. That's right. Has no couth.
Because
Right.
when I was in fifth
Uses
grade,
the salad
there was
fork when it's not supposed to. Yes.
weird typo in the book, and they had to change it. But I don't. It was weird because it wasn't improper fraction, but.
Top heavy sometimes, which I don't really like using that terminology. You hear top. I've heard teachers say top heavy fractions. Maybe don't go there. How do you turn this into a mixed number?
Would you divide it?
Yeah, one way to do it is divide, right? And you get the remainder and all that kind of stuff. So if I do that, 7 goes into 11 once, 4 left over. So instead of writing the big ass R, now let me show you something kind of cool. What number below 11 do you wish was up here instead? 7. You guys agree with me? If that was 7 over 7, wouldn't that be like, give me plenty of those, right? What is 11? Isn't it 7 plus 4?
Yes.
What is 7 divided by 7? What's 4 divided by 7?
7.
Neato.
Yeah.
I'm sorry.
Neato. Isn't this capturing what remainder means?
Yeah.
It's how much extra there was. Have you guys ever seen that before? It sounds like no.
No, we only saw the one with the dividing, that's it.
Yeah, let's do one more. Watch. So what about something bigger? Let's say 38 over 11. You guys, let's see if you guys can do it. So you could divide it, but
How'd you get 4? Is that how it's just between?
I wanted a 7, but 11
Yeah,
is
so
7
it's
plus 4. I
okay.
can't just replace it with a 7. So what do I wish was up here that's right below
What
38?
is 7? Oh, well, no, you don't.
Because of the 11, I wish there was a what? Right below 38. What number do I wish was here? 33, yes? Because 11 goes into it. So this is 33 plus 5. So this will be
What?
3 and 5 11s.
Wait, what?
What?
Where'd you get 33 from?
All right.
Yeah,
Oh.
So again, why does 38 suck? Because 11 does not go into it, yes?
Yeah.
So it just sort of inherently sucks. What number below 38 do I wish was up there? If I could just pick 33, yes?
Can you
Because 33 is divisible by 11. You guys with me? But I can't just put a 33 here. I can't just say, I like your question, but let me make a new one, Jeff. I've had students kind of do that
and you
before.
would add it to get, okay.
So 33 plus 5 is 38. So I haven't changed the problem at all. I've just made it look different. But now I can see that's 3. And I can see that's 5 11s. Okay. I really like that. Oh, to be honest, it's not like quicker. You know, sort of. It's not really quicker. It is kind of quicker because you write a little bit less. But it's just cool to see another way to do something. I don't know if you guys agree with me or not.
Yes, sir.
By the way, last statement. This,
I don't believe you anymore.
I understand. I don't blame you. I don't blame you. If I do any more after this, you can just walk out. This notation sucks. Why does this notation suck? What is really in the middle? Is it times? Is that 3 times 5 11s?
No, it's
Hell no, because that would be 15 11s, which is not what it is. What's in here really?
a plus.
A plus, right? You can see it here. But we just chose, not we, because I was not a part of this decision. I'm not that old for one thing, because it was centuries ago. They decided this is just the way we're going to write it, and it's like, what do you tell students when they get to algebra? Oh, if it's sitting next to each other, it means times. And then you have this shit floating around, and students are like, okay, math sucks, and you're like, oh god. So it's too bad we got bad notation. So just make sure your students understand that if you do talk about mixed numbers with them. That's enough. So next time we'll play with little hexagons and stuff. We'll look forward to that.
Okay.